Okay, so today we are going to start from where we left yesterday. I'm Rohit, connected from Dr. Roshan's mobile here, presenting from my window. So here we will start and cover all those aspects which lie beyond my previous lecture, that is the 5G communication RAN. And there is one more announcement for the evening lectures. So, Dr. Aryan Kaushik, uh, who is an expert in 5G and 6G wireless communication aspects, will be presenting today because of some tight schedule tomorrow. So today we are going to have two sessions. One session is from Dr. Aryan Kaushik. Another session is from Dr. Nishant Gupta. So in the evening we are having two sessions. One session from one section via Dr. Aryan Kaushik will be held from 2 to 3:30, and another session from 3:30 to 5 p.m. Dr. Nishant Gupta will be presented. Let's start today's session. I turn off my video for bandwidth saving. Okay. So yesterday we have gone through. First of all, is there any query regarding the yesterday's lecture? Yesterday we have covered a lot of aspects related to 5G communication, 3G, 2G, and first generation. What are the basic aspects and requisites of a communication system? How the how the capabilities and the potential can be increased of a 5G user. Am I audible to you? My voice is clear.
Yes, sir.
Yeah. Okay. So yesterday we have gone through some innovative aspects, how we can assign more and more resources to a user, and how data rate is being increased, how the bandwidth is being increased, how we can assign multiple channels and time slots to a single user in order for the sake of increasing data rate. So also we have shown we have discussed about the wireless communication aspects, what's happening between the base station and okay, let me turn on my video. Okay, so what happens between the base stations to a user? So all these aspects, what happens within this wireless channel, we have gone through, and on the basis of that we divided the whole wireless communication scenario into two subparts. First one is wireless and next one is radio access network. So today we will have a discussion regarding what a radio access network does, how it is being evolved. Also, I plan to have some MATLAB exercise in my session, but for that we are having some dedicated experts from the MATLAB. So today, as per your request, I tried to cover some of the innovative topics in 5G and 6G. First one is intelligent reflecting surfaces, and next I'm covering dual function radar communication today. So after the RAN evolution, we will discuss about intelligent reflecting surfaces and DSRC techniques. So this we have already gone through. This is a RAN. This is a general RAN which connects you or a user equipment, that is a mobile, to a core network. This we have gone through, and also we have discussed that the way we are communicating to the base station also affects the core network. That is the reason why the RAN architecture is being renamed and evolved with the generations. The second generation RAN is known as GSM RAN because it is based on GSM architecture. Next generation, that is 2.5 generation, is based on GSM HRAN. GSM HRAN stands for GERAN, which is for 2.5G communication and is based on EDGE, enhanced data rate for GSM evolution. Next we have universal terrestrial radio access network, that is based on third generation communication system. So can anyone tell why we are referring this network, third generation network, a universal terrestrial radio access network? Any idea? Okay, so let me answer this question. So universal terrestrial radio access network, third generation network. Okay, we are having some answers here. Yes, same band everywhere, roaming was introduced. Yeah, partially correct, because by the end of 2000, we intended to have an standardization so that we allow roaming and global, say, global harmonization, I can say. So all the nations and all the countries should follow a same standard, a universal standard. That's why it is known as universal terrestrial radio access network. In the next generation, that is the fourth generation, utran network has been evolved a bit, and that's why it is known as evolved universal terrestrial radio access network, या फिर utran. Now coming to the equipment, what reside within at the UE side and core network side and radio network side, we have also already discussed this. Yes. Also, we have discussed about the basic base station architecture. In a base station architecture, obviously we are having some antennas, some radio unit that is responsible for all radio operation, including modulation, multiplexing, etc. And also for processing, we are having some baseband unit. Baseband units are responsible for. Can anyone tell baseband unit? What are the tasks of baseband unit? You can turn on your mic and answer. Any idea? What are the tasks of baseband unit? No. Okay, so baseband unit is responsible for all sort of processing required in communication. Next, we have also discussed about DAC and ADC. These are some essential unit for converting your data message from digital to analog, and at the receiver end we need to perform the reverse of it. So can you tell anyone is having any idea why we perform ADC and DAC? Okay, so I'll answer that question if you ask me again. Now coming to the RAN architecture. First generation RAN is a basic RAN that connects you to the user terminal to the core network, which is in the case is MSC, mobile station controller. Mobile station controller is basically controls the base station, and which base station also reside VSC operation, base station controller as well. In the second generation, these two entities have been segregated. In the second generation, there is a air interface that connects user to the BSC and BSC control base transceiver system. So base transceiver station is connected to the BSC by a UE, and BSC is responsible for all controlling operations that are associated to BTS. And at the back end, we are having MSC, which again at the back end controls the operation of BSCs. So this sort of network only can only support the voice communication. In order to support the data and packets, we have to include one more unit here. This is responsible for transmitting your packets. So therefore, in addition to your voice, which travels with this path, now you can transfer your data or messages as well via this network. So this again, let's have a quick overview of the 2G architecture. Here in the 2G architecture, this that goes from top to the bottom, and at the top you are having a mobile terminal. Mobile terminal is connected to the BTS base transceiver station via air interface that is known as UM. UM is the air interface, and at the back end, which is controlled by BSC and MSC, and different MSCs can communicate together to establish a call. And also we are having some different registers here. So what are the operations of HLR? HLR stands for anyone? Okay. HLR stands for home location register that carries all the entries of users lying within the intended or authenticated registered cellular network cellular regions only. Now coming to the next GRAN interface. GRAN interface. So here we will discuss only about this air interface, how it establishes a communication network between the mobile user terminal and BTS base transceiver station. So here we have shown that already we discussed this in the frequency. Via dividing the whole frequency band into a smaller number of chunks, we can have up to 124 channels for uplink and 124 channels for downlink. And these frequency bands again orthogonalize in time domain, where each frame that consists of that is of duration 4.615 millisecond again bifurcate or divide the whole slot into whole frame into 8 number of slots. So that makes the duration of each slot, the time slot, roughly equals to 577 microseconds. So a small part of this time is allocated as a guard band, so that the bits coming from the previous frame may not interfere to the bits at the next frame. So the guard band duration is 577 microsecond minus 546.5 microsecond. So this is the difference that is allocated for the guard band, and half of that is allocated to the left side, half of that is allocated towards the right side. That means 15.25 at each side is allocated to mitigate the effect of delay that could be occurred with the previous framed bits. Now coming to the next aspect, the spectrum we have already discussed, separation, the data rate. Within this frame we are having 3 bits for tail here, so 26 training bits, and S stands for status, uplink or downlink transmission is being carried out. So out of one possibility, 1 or 0, 1 indicates uplink and one indicates downlink. So we are having a user data 57 bits plus 57 bits are the original or user data which is being transmitted from within this duration. So in a time slot of 577 microsecond, we are transmitting 57 plus 57 equals 114 bits. Each slot, one slot is allocated to each user only within the duration 4.615. That means within this duration we can transmit only 114 bits in each 4.615 milliseconds. So that makes a data rate of between 20 to 30 kbps. So data rate in second generation was limited to some 20 to 30 kbps only. Now coming to the other aspect, as shown in this structure, As one user moves from one cell to another cell, so a sort of handoff is also there. Suppose a user is moving from this cell to this cell. So as soon as the user comes into the vicinity of new base station, all the controlling operation or serving capabilities should be shifted to the new base station. This is known as handoff, and all handoff operations are being taken care by BSCs connected to the to both the base stations. And if the user enters into a new cell that belongs to a new MSC, handoff operations are to be carried out by MSCs also. So in that case, MSCs are being intended, and visitor location register is assigned a new entry for the newly entered user. So these are all other aspects which are essential for communication: access control, authentication, confidentiality, and anonymity. So this I will share with you. You can have a look at this. So again, this is another architecture, 2.5G architecture. We have already given an overview. Now coming to the new architecture, Universal Terrestrial Radio Access Network. UTRAN is experiencing some sort of enhancement in terms of functionalities. Here you can see BTS now becomes Node B. So all the base stations have got a nomenclature of Node B, and BSC, which is responsible for controlling operation, is now indicated as RNC, that is Radio Network Controller. And in the third generation, or in UTRAN, this was the first attempt to make the thing centralized. So what are the benefits of centralized unit? We will discuss in the subsequent slide. So this was the first attempt to make the thing centralized. So here you can see a simplified architecture where all the controlling operations have been shifted to RNC. So RNC is nothing but an entity that is very similar to the base station controller. Node B is nothing but a base station and very similar to the BTS with a new nomenclature and some add-on capabilities as well. So let's have a brief discussion about UTRAN, that is third generation communication network. So everything discussed in this slide can be simplified into three architecture, three boxes I could say. So first one is user equipment. So here user equipment is residing, which is connected to the node Bs or radio network via wireless interface. So in this case, wireless interface is indicated as UU. That is connected to the universal RAN, that is UTRAN, and UTRAN is connected to the core network via interface IU. So UTRAN handles cell level mobility, comprises several radio network subsystems. So first one is function of UTRAN is channel ciphering, deciphering, handover control, radio resource management, which is very similar to the previous generation's operation. Links are now become UU. Earlier, the air interface between the user and the base station was known as UM. Now it becomes UU. And next interface, that IU, earlier it was referred as interface A between the base station and core unit. So these have been evolved. Again, why these changes are being made? Just to increase the capability of the network. Next major change is noted here. Again, as I told earlier, base station in cellular network are termed as node B. Node B is controlled by RNC. RNC in 3G network performs similar operation that has been performed by BSC in the earlier networks, previous generation networks. In general and overall, UTRAN, some centralized function exist, and this is the first step, as I mentioned, towards the centralized network. Yes. So rough mobile, which is discussed. and next one is the serving network domain, or we can say core network domain, which also contains home location register and visitor location register with some new names. Now again let's have a quick overview. What happens, what are the changes that has been occurred between the user equipment and node B. So this interface is again wireless interface. We have already gone through the frame structure, how the frame structure looks like in the second generation. Let's have a look how the communication is being established between the base station to the user equipment in the third generation. So here in the second generation, time slots are the entities which have been utilized for the orthogonality, to achieve orthogonality between the users. Now in this case, in third generation, codes are responsible to provide orthogonality among the users. For example, if one user is assigned a code XX, another user will be assigned a code X minus X, so that if X is multiplied with X, next X is multiplied with minus X, their summation should be 0. For example, let's say you are having this is how a code is being generated. So if in this scenario, in a scenario where there is only one user that is intended or request for the access, wireless access, you can assign, you don't have to make any change, because there is only one user and there is no chance of collision or spectrum sharing. But suppose there are two users. So in order to serve two users over the same time and frequency band, you need to assign two orthogonal codes to different users. So in that case, first user will assign 1 1, next user will assign 1 comma minus 1. So the user with 1 comma 1, if it receives signal of user 2, that will be multiplied with this code 1 will be multiplied with 1, next one will be multiplied with minus 1, and due to the multiplication, these addition will cancel out. 1 minus 1 equals to 0. These addition will cancel out the impact of interference from the different user. So doing this, we can support multiple number of users. But here, in the case of one user, we were transmitting only one symbol. In the case of two users, we have to transmit two symbols. Therefore, the bandwidth requirement increases, and therefore this is known as spreading code multiple access. Spread code multiple access and direct sequence spread spectrum techniques, where different orthogonal codes are assigned to different users to provide orthogonality. So intuitively, can you suggest what are the limitations or disadvantages or the things we need to take care in this generation, third generation? What are the limitations, disadvantages of this technique? You can post your answer or you can turn on your mic. Yeah, home location register, roaming version. Yes. So anyone is having any idea what are the other effects of this transmission scheme? Okay, no response. So 1 minute. I'm joining in 1 minute. I just need to take an urgent call. Sorry for the inconvenience. Yeah. So any idea about the other inference of this transmission scheme? So okay, let's discuss about it. So as bandwidth expansion, yes, very correct. Bandwidth expansion is one aspect, or we can say that in order to support same data rate, we need to have a double bandwidth. And conversely, we can say that if a user, if we are shifting from one user scenario to two user scenario, and if we do not have any bandwidth expansion available, we can divide the data rate. So we can assign half bandwidth to the user, or half of the resources to user 1 and half of the resources to user 2. In other words, what I'm trying to say is shifting towards the right in a tree make your data rate half. So data rate assigned to user 1, in this case to a single user, will divide the data rate half in each branch. So in the case of two user, the data rate is divided into two halves. So the number of ones as the length of this code is being increased, the data rate is being divided. So in case of SF4 spreading factor 4, the data rate will be 1/4 of the data rate that is being provided to the user 1 in case of SF1. So moving towards the right increases the number of users, but it decreases the overall capability that is being assigned to each and every user. So how can you provide a dynamic data rate to a user? For example, one user requires 4 Mbps, another user requires 8 Mbps. Is there any scheme you can adopt from this tree to assign both, to fulfill the requirement of both the users? Any response? Okay, let me answer this question. So if a user being assigned 1 comma minus 1, that means it can sustain a data rate, let's say r mbps, yeah, r bits megabits per second. And another user, if he or she is assigned this code 1 minus 1 1 minus 1 of length 4, the data rate will be of r by 2 mbps, yeah, r by 2 megabit per second. So if one user wants a code that is double, data rate that is double the assigned bandwidth, so you need to cut the tree here only. You do not need to divide the link capacity further. So if one user requires a data rate r, he or she should be assigned SF1. If one user requires data rate r by 2, he or she should be assigned a SF2. And similarly, if a user requires a data rate r by 8, you can assign SF8 or spreading factor 8 code to that particular user. This is how you can control the data rate of a user. So any doubt so far?
Sorry, could you explain again? I got a bit confused.
Sorry. Hello?
Can you hear me?
Yeah, I can hear you now.
Yeah. So the explanation, could you just repeat it again? I got a bit confused. Yeah. Especially when you said if one user needs double data rates after this 111, we don't need to, the tree doesn't continue. That's why I got a bit confused. Yeah.
Sorry, I'm not getting your question. Can you repeat it again?
You know what I'm saying? For UT-RAN, yeah,
Yeah.
when you have two users, one user needs double data rate. What's the technique? That's where I didn't understand again. Could you repeat from there?
Yeah. So what happens when we construct this tree? So if there is one user that requires R Mbps, let's say the whole capability that the network could assign to a user to any user is R Mbps per second. So R is the maximum capability. So if the quality of service requirement of a user is R by 2, we can assign 1 comma 1, or we can assign a code that is from this code tree 1 comma 1 or 1 comma minus 1. Anything could be assigned. But if the user's requirement is R by 8, we can go up to this SF8 spreading factor. So we can assign one of the code in this code tree that belongs to SF8 with length 8. Are you getting the sense? Is it clear now? I think he's not available. So we can move ahead and we can take question later on. Now, this is the frame structure of UTRAN. So we have already gone through the frame structure of second generation communication system. In the now that is this slot frame is also very similar to the second generation frame, but in this case we are having a frame duration of 10 millisecond. In the previous case we were having a frame duration of 4 point something millisecond. So that was being divided into 8 number of time slots, but in this case the users are not being orthogonalized in time domain. So in this case users are being orthogonalized in code domain. So here in 10 millisecond we have 15, that is ranging from 0 1 2 3 up to 14 time slots. So we have 15 time slots. 10 millisecond divided by 15 equals to 666.7 microsecond. So within this duration we can assign a slot to a user. Also we can assign multiple slots. So let's say if we assign one slot to a user, what happens? So the slot, again, each slot can carry multiple type of data. For example, DPCSH, data packet channel, and DPCH, uplink and downlink data, or या फिर data first thing is uplink and second thing is downlink. So in the uplink direction we can have either data or we can have controlling channels. So we are more interested in getting how much data rate we can attain. So let's discuss about this frame which is illustrated in between these two slots. So time slot in WCDMA, also this is known as WCDMA. Why? Due to the bandwidth expansion. So in this case we are transmitting a symbol multiplied with a spreading sequence. That's why it is also known as WCDMA. So time slot in WCDMA or UTRAN frame are not used for user separation, because this is not TDMA, this is CDMA. And radio frame consists of 38,400 chips. So in case so these sequences are also known as chips. So here SF8 means 8 chips belongs confines that, or which means that 8 chips are being transmitted to transmit one symbol. Here SF4 means 4 chips or 4 length bit are transmitted to share one symbol. Similarly, SF2 means in order to transmit one bit or one symbol, we are multiplying 2 chips. So total number of chips in a radio frame consists of 38,400. So these are the number of chips available for whole frame structure. Thank you. Okay, so roughly in one slot, the number of chips are 38,400 divided by 15. And it roughly carries a bandwidth of 4.4 to 5 megahertz. Now, we can leave this point. Next one important point is the spreading factor of this channel can vary from 4 to 256. So in this code tree, as I shown, so SF1 is not allowed, SF2 is not allowed. Minimum SF allowed is SF4. Maximum SF, spreading factor allowed is 256. So let's see what could have been the maximum and minimum data rate for a user. So number of chips available with each slot is 38,400 divided by 15. That is equals to 2560 chips in each slot. So each slot can transmit 2056 chips in 666.7 microsecond. So in 666.7 microsecond, we can transmit these much of chips. And if 4 chips carries 1 data, that means for SF spreading factor 4, if 4 chips carries 1 bit, that means in this duration 666.7, we can transmit 2560 divided by 4 number of bits in this whole slot. So this slot can carry maximum data bits 2560 divided by 4, and minimum data bits that could be transmitted over this slot is 2560 divided by the maximum spreading factor, that is equals to 256. So with this, you can have a data rate up to 960 kbps. So in this duration, roughly 666 microsecond, you can have a maximum data rate of 2560 divided by 4 bits, and in 1 second you can have 950 kbps if you calculate the same. Similarly, with the maximum spreading factor 256, you can transmit a data rate of 666.7 2560 divided by 16 bits in this 666 microsecond. So in 1 second you can directly convert, you can have a data rate of 15 kbps. So is there any doubt with this? This is simple calculation. Multiplication and division you can directly perform. Any doubt so far?
No, sir, it's clear.
Okay. Yeah, now coming to the next generation RAN, that is fourth generation centralized RAN, towards the centralized RAN. So this is the best example where we have moved towards the centralized RAN. So fourth generation RAN, which is also known as enhanced UTRAN, is the another big step towards the centralized RAN, I could say. So here we are getting some more essential things. Again, the user equipment is connected to the base station. Base station in third generation was known as Node B. Now it is known as enhanced Node B. Enhanced Node B. So functionalities are similar. The function which has been carried out of base station now being carried out by eNode B. eNode B, because it can now support some of the additional functionalities or enhanced functionalities. So it becomes eNode B, and user equipment is again connected via radio interface, and we get some more entities within the core network here. So I have summarized this in this slide. This I will share with you. You can go through it. But the crisp is, in contrast to GRAN and UTRAN, which uses a combination of base station and controller of RAN, ETRAN uses eNode B. Nearly all part of RNC are incorporated in eNode B, which is again very obvious, but the biggest thing we have seen till now, or we have observed till now, at each cell site we need to have a base station that covers transmitters in the form of antennas, a radio unit, as well as baseband unit for communication or for signal processing. So each base station till the fourth generation, each base station covers radio unit, baseband unit, and obviously antennas are there. So all the cell site cover these three entities. Therefore, this sort of base station or radio units are known as distributed unit, because at each cell site you are having these three entities available. Can you combine one of the entities to cover the operation of multiple cells? Can we combine this baseband unit for the computation of multiple cells? Let's say this baseband unit is not connected to a single tower. It may connect it to multiple tower to perform the computation of multiple towers. The answer is yes. So we can centralize some of the operation, but till now, up to the fourth generation, all the architecture we have seen are distributed in nature. So distributed RAN, which is also known as DRAN, have some limitations. So first one is the cell maintenance. Because all the cell sites are carrying all the units, even if one unit is having some problem, we need to shift our unit or maintenance team to the cell site of intended cell or cellular structure. Next one is compatibility. Still, if you see this architecture is also having some proprietary issues. Let's say you have you bought some unit RRH from one company. You need to have BBU from the same vendor. Also, you need to have this connection link from the same vendor. This is known as proprietary lock-in or vendor lock-in. That means if you had one unit from one vendor, you need to have all the units from the same vendor. This is known as vendor lock-in. So in terms of vendor lock-in and proprietary flexibility, we are now shifting towards, so fourth generation architecture network is having some flexibility in terms of connection link are not proprietary, and some other units are not proprietary as well. So but the network is still again not pure fully open. Fully open means we should not have, or we should not buy something from the same vendor. We should not lock in ourselves towards a single proprietary vendor. So these are some limitation. Cost, obviously, cost is another factor, because all the cell network or cell site are covering these three aspects. Baseband unit, which is very costly. So baseband unit is essential for all cell site. So for all cell site, we need to implement or install baseband unit, dedicated baseband unit. So these are some limitations of DRAN. So how can we mitigate such limitations? Via implementation of different RANs. So here we have DRAN. Please look at this figure very carefully. So this is one shown here is DRAN. With the DRAN, we are having at each base station we are having radio unit, antennas, and BBU unit, that is baseband unit dedicated to the cell site. So antenna, RRU, BBU, all are available to the cell site in the DRAN. In the case of CRAN, that is a centralized RAN, what we are doing, we are sharing the same backhaul network and same BBU unit. So BBU unit is now being shared between multiple cellular structure cell sites. So same BBU is being utilized for this base station as well as for this base station. So this is known as the concept of centralized RAN, where some pooling of the computation units are being done. So since we are centralizing the computation, computation unit. This is known as centralized RAN. Another nomenclature for CRAN, obviously and very frequently used is Cloud RAN. But Cloud RAN, Cloud RAN is different from this centralized RAN. Now coming to the virtual RAN. In virtual RAN, we are again making some of the functions that should be available on demand and should be available on the cloud. So why we are doing so? So that those functionality and those operation, those resources should be available at the cloud and can be get on demand. So that we should not assign such capabilities within the base station itself. So we are centralizing things. As we are moving towards the 5th generation, 6th generation, we are centralizing things. Again, Open RAN, within the Open RAN, everything is open. No proprietary lock-in is there. So anyone, any company, any vendor can be called to set up a network. Also, they need to follow some standard. The standard would also be uniform. So you do not have to have some vendor lock-in. You can ask anyone to make any connection here. So 5G in terms of network is providing very much flexibility. Any doubt with this? Any query? Okay, no query. I have listed here some of the benefits and some of the key features of DRAN, CRAN, virtual RAN, and Open RAN. You can go through it, and you will have the access of it. I have all the main points and key points I have already discussed. So vendor interoperability, open APIs, RAN cloudification, everything is being supported in ORAN. You can get a look at it. Now coming to the 5G new radio, let's discuss some of the essential aspects of 5G radio. This is how a simplified 5G architecture would look like. This picture. First of all, this has not been built by me. This picture credit goes to slide team, from where I have copied this, and you can see in this figure, especially look at the do not look at the core network, look at the base stations. Some of the base stations are being named as G node P, and some of the base stations are known as new generation E node B. So as the generations are keep on evolving, the second generation base stations were known as BTS, third generation base stations were known as ENB, third generation base stations are known as Node B, fourth generation station are known as E Node B, and fifth generation base stations are known as G Node B. Here in this case, you are having G Node B. G Node B are the base station which can support all the functionalities that are available for 5G structure. All the functionalities could be supported in G Node B. But look at the NG E Node B. NG E Node B are the fourth generation network or fourth generation base stations, but they can support some of the possible aspect of 5G. So they are not either fully 4G, not either fully 5G. So they can support some of the functionalities of 5G, and they are also known as next generation E Node B. So again, they are E Node B itself, but they can support some of the next generation function and are referred as next generation E Node B. And again, all such G Node B, E Node B are connected to the base station to the mobile via wireless interface. Now coming to the next essential aspect of 5G communication, that is the frequency band. What are the frequency band available for communication in 5G? So if we roughly divide the whole frequency band into some smaller number of parts, we can roughly say that low band is a band that varies from some hundreds of megahertz to 1 gigahertz. This is known as low band. And if you look at the frame structure, and the very first generation and second generation also was based on 700 or 800 megahertz spectrum. So this was the operating frequency of second generation, and we worked on, and the channel bandwidth per user was 30 kilohertz in that case. So this low band can support and has been supporting the second generation of wireless communication system. And obviously, as 3G came into the picture, this band was also available for third generation of communication system if the resources are available and a user obviously is having a 3G mobile phone. So if a band is available for 2G, obviously it will be available for 3G, 4G and 5G based on the resource availability and your mobile supportability. So this band was intentionally utilized for second generation and was available for third generation, fourth generation and fifth generation based on your technological support and spectrum availability. Next band is low mid band that varies from 1 gigahertz to 2.6 gigahertz, and this was available for third generation. So 2G cannot be supported within this band. So this band was available for third generation, and obviously it was later available for fourth generation and now fifth generation as well. So if most of the mobile phones within the cell vicinity are 4G, we cannot shift it towards the 5G until and unless our mobile cannot support the 5G operation. So again, this band was available for 3G and now is available for 4G and 5G as well. Mid-band. Mid-band varies from 3.5 gigahertz to 7.1 gigahertz, or this is also roughly known as sub 6 gigahertz band or sub 7 gigahertz band. So here 4G and 5G operations can be carried out. And one special band in this case is N78 that varies from 3.3 to 3.8 gigahertz. So this band is usually come free for research purposes, and most of the research is being done on 5G within this band only. Now coming to the higher band. Higher band, also referred to as millimeter wave band, varies from 24 gigahertz to 52 gigahertz, and that is available for 5G communication. Again, what is the need for higher band? Because 5G supports critical application that requires data rate in Gbps, not in Mbps. In Gbps, so that we need to have a higher frequency band available, and bandwidth availability is also required. So this millimeter wave band is available for such 5G applications. So you may wonder, if we have this much of bandwidth availability, why we are looking at the possibility of using this low band and low mid band for 5G applications? Can anyone answer this question? Why we still looking for lower frequency bands if we are having such wideband available? Anyone?
For coverage?
Yes, sir. Please say.
For coverage?
Yeah. So smaller frequency bands have wider coverage and better reliability of communication. Also, for some of the low data rate application, for example, smartwatch and some other industrial application which requires very small data rate, those application could be supported at these smaller bands. Yeah, so the answer is correct. For such critical application, we can have high band. Also, there are some issues available with the millimeter wave transmission. Millimeter wave communication cannot be easily established because the millimeter wave alternates very fast. It cannot travel very large distance, and usually the communication should be line of sight. Yes, high propagation loss. Hamza, you are correct. Yes, high propagation loss are there. Therefore, beamforming is usually done in the high frequency band millimeter wave. Directional communication, yes. So beamforming and directional communication is to be done within this high frequency band. So therefore, we cannot support high data rate very easily. We need to perform some sort of pre-processing before the real transmission in high frequency band, and we can say that some pre-communication or pre-processing is to be done for beam formation. Now you could wonder who is the one or any organization who are they which is specifying these frequency bands for different operations and for different communication standards generations. So this is ITU, International Telecommunication Union, defines these limitations, or I could say standardizations that could be universally adopted for the mobile communication so that your mobility could be saved. So in the recent conference, this World Radio Conference happens to be in 4 year, once in a 4 year. So in the latest one, 2019, they identified these bands for operation. So now the bandwidth availability for 5G is increased up to 17.25 spectrum, 17.25 gigahertz spectrum. So it is based on the country. You can wonder, does anyone need to forcefully follow these standardization? Not forcefully, but usually most of the countries follow this one because everyone wants to have their universal adaptation for mobility. So almost all the countries follow this standard. And next concern is whether these frequency bands are easily available or freely available. So that depends on the country. So because these are some resources that belongs to a country or a nation or the government can sell these spectrum and can make money out of these. So some of the frequency bands are maybe available for research purposes, free for use, or they could be available at a very nominal cost for the academic and research purposes. And next one is, can we have another division or classification of frequency? Yes. So roughly the whole frequency band is divided into two categories. Usually we have heard of sub 6 gigahertz, sub 7 gigahertz. So up to release 16, you want to say something? Anyone? Okay. So up to release 16, there have been a support for 6 gigahertz available only. So usually we used to term it as sub 6 gigahertz frequency band. After that, we can now use up to 7.125 gigahertz frequency band. So now it is being termed as sub 7 gigahertz band. So FR1, frequency range 1, roughly covers the frequency band that starts from 410 megahertz to 7.125 gigahertz. And next frequency band is known as FR2, which usually covers millimeter wave and varies from 24.25 to 52.5 gigahertz. So this is the frequency band I have shown. So we have already discussed this. FR1, FR2, we have discussed. FR1 varies from roughly. We have already mentioned these frequency bands. Now coming to the channel bandwidth. What are the channel bandwidth available? So as in the case of FR1, frequency range 1, lower frequency bands are allocated here. Therefore, the bandwidth availability is also lower. So here, for within the FR1, we can have a bandwidth from 5 megahertz to 100 megahertz. And in case of FR2, we can have a bandwidth 50 megahertz to 400 megahertz. So we can have varying within this 5 megahertz to 100 megahertz, we can have 5, 10, 15, 20, 25, and so on. And within this FR2, we can have 50 to 400. So 50, 100, 200, 400 we can have. And again, if we divide different wireless generation on the basis of their multiple access techniques, so first generation was FDMA, second generation TDMA, third generation CDMA, fourth generation is OFDMA, orthogonal frequency division multiple access. So any doubt so far? Next we are going towards the famous structure of fifth generation or orthogonality, numerology in fifth generation. Any doubt so far?
No, sir. The only thing is why are we calling sub gigahertz sub? What is this meaning sub? Why
Yes. Okay,
don't
so
we call gigahertz 6 gigahertz band, 7 gigahertz band? This sub means what?
sub if you directly say 6 gigahertz, that indicates only one frequency band, that is 6. Not left to the 6, not right to the 6. Sub means below 6 as well. If you say sub 6, that means 6 including 6 and below 6. If you say above 6, that means 6 and above. So below 6 and above 6, that is being represented. These are two terms. So below 6, we generally say sub 6.
Okay, sir.
Now coming to the numerology. In the previous 4G cases, we have gone through. We generally use OFDM. OFDM is a multiple access technique where we use overlapped frequency spectrum. Overlapped spectrum we have. You must have been shown. So the difference between two carriers is 15 kilohertz. That is fixed for fourth generation. But in fifth generation, what we are trying to do is so that the user could be adopted from 15 kilohertz to 30 kilohertz, 60 kilohertz, 120 kilohertz, 240 kilohertz based on the available bandwidth availability. Getting it? So in the fifth generation, we can have multiple numerologies. So how do we assign different numerologies? So the slot duration in the previous case was 1 millisecond, which supports a subcarrier spacing of 15 kilohertz. That means in a 1 millisecond, whatever we could transmit over this subcarriers, which is having a distance between two closely consecutive carriers is 15 kilohertz. So if we're trying to increase this bandwidth, we can double this. We can double this and we can move from 15 to 30. So whatever we were transmitting in 1 millisecond, since bandwidth is now doubled, we can now transmit in 0.5 millisecond. So if we keep on increasing the assigned bandwidth, the transmission time decreases. So this is how we can reduce the latency. If your application is very critical, you can now decrease the bandwidth. You can now decrease the time via increasing the bandwidth. So you have to increase the bandwidth, and your subcarrier spacing will be increasing in frequency domain. So in time domain, you are shrinking the time or latency. In frequency domain, you are increasing the subcarrier spacing or usable bandwidth. So here, what you can do, numerologies, you can have 4 numerology, one with 15, one with 30, one with 60, 120 and 240. You can have 0, 1, 2, 3, 4, 5 numerologies, which are denoted by a symbol mu. So for mu equals to 0, so this is how it is increased, 2 raised to power mu into 15. For mu equals to 0, the bandwidth separation is 15. For mu equal 1, bandwidth separation is 30. That means bandwidth separation is equals to subcarrier spacing between two carriers. So if you keep on increasing up to 4, your subcarrier spacing becomes 240. And one resource in each numerology carries 12 subcarriers. So one resource block, as indicated here, one resource block, each resource block carries 12 consecutive subcarriers. So for numerology 1, the subcarrier spacing is 15. Numerology 0, subcarrier spacing is 15, and the resource block could carry 12 resources which are separated by 15. So the whole frequency range is 15 cross 12 equals to whatever it is, roughly 180 kilohertz resource block. So accordingly, the bandwidth consists of subcarrier spacing into 12 into the number of resources. So one resource carries 15, one resource carries into 12 into the band subcarrier spacing, and if you keep on increasing the number of resources, your bandwidth will keep on increasing. So here is one example. For mu equal to 2, the subcarrier spacing is 60. And if 100 megahertz channel bandwidth is available, 100 megahertz channel bandwidth is available, guard band is 1370 at both sides. So the total transmission bandwidth is equal to 100 megahertz minus 1370 left side, 1370 right side kilohertz. That is being separated, and available transmission bandwidth will be divided in number of channels. So the one resource for mu equal to 2 equals to, for numerology, that is mu equals to 2, one resource block will carry 60 kilohertz into 12. So so the answer is, number of subcarriers here is bandwidth minus 2 guard band, one for left side, one for right side, divided by SCS. SCS is equals to 60 for mu equals to 2. The number of subcarriers are bandwidth minus 2 GB divided by SCS, that is 60, equals to 1621. You can perform this calculation. These much of resources are available. Resource bank are number of resources divided by 12, because one resource bank carries 12 subcarriers. And again, what are the transmission mechanisms and modulation techniques included? So 5G adopts a situational aware modulation technique. You can have the access of QPSK, 16 QAM, 64 QAM based on your channel condition. If your channel condition is very good, your constellation diagram points may come very closer. So you can transmit up to 256 QAM. If your channel condition is very poor, you can decrease this constellation space up to QPSK. Now coming to the bandwidth calculation. So you can perform some sort of calculation. So bandwidth availability in FR1. So if a subcarrier spacing is 15, that is mu equals to 0. So one resource block will carry for 15. One resource block will carry 15 into 12, and 25 resource block will carry 15 kilo into 12 into 25. That is roughly equals to 48. That is roughly equal to 4.8 megahertz, and shown here as bandwidth equals to 5 megahertz. If you double the number of resources, your bandwidth becomes 9.8 megahertz. That is roughly equals to 10 megahertz. And this is how you keep on increasing. And your bandwidth may, in the numerology 1, your bandwidth may go up to this 50 megahertz. And in case of numerology 2, your bandwidth may go up to 100 megahertz. So for FR1, you can have minimum bandwidth 5 megahertz, maximum bandwidth 100 megahertz. Now coming to the FR2, frequency range 2, the bandwidth can be calculated as, so mu equals to 2. So FR2 can support, FR2 could be supported in numerology 2 as well. So for numerology 2, we can use FR2. Numerology 3 and 4, we can also use FR2. So in case of FR2, the subcarrier spacing is 2 raised to power 2 into 15, that is equals to 60. 60 kilohertz into 12 gives you the resource bank. So 60 kilohertz into 12 into the number of resources 66 is roughly equals to 50 megahertz. So this is the bandwidth available, bandwidth required for FR2 transmission. And if you keep on doubling this number, your bandwidth will keep on increasing. So your minimum usable bandwidth in case of numerology, FR2 case is 50 and maximum is 200. So here in case of FR4, you can go up to 400 megahertz. For FR3 as well, you can go up to 400 megahertz. So FR4, there is one note. FR4 is not available for data communication. These bands are up to release 16. These bands are available for channel transmission only. Some signaling and channel transmission. evolving technologies. So with this, we have concluded some of the basic operations and basic aspects of 5G communication. Any doubts so far? Because I'm going to discuss about some evolving techniques, including intelligent reflecting surfaces and dual function radar communication. Because yesterday we have received some comments and some requests regarding some discussion on intelligent reflecting surfaces. So any doubt so far when in 5G communication aspects, frequency bands, their architecture, anything?
No, sir. It's fine till now.
Okay, so I think no one is having any doubt. So we can go ahead with the evolving technologies. So first, let us look what are the challenges associated with millimeter wave transmission and what are the prerequisites of beamforming. Okay, if you look at this figure, here you can see there are two users which are intended to be transmitted over millimeter wave, not the microwave, over millimeter wave. So as I told earlier, millimeter wave attenuates very faster. They have very limited transmission range, but they possess enormous bandwidth there. That's why even if the communication duration is very small, you can have very high data rate. So, but the challenge is you need to transmit you need to make a communication in the form of beams only. So before the real transmission happens, you need to find the real direction of beam, and you need to perform some sort of pre-processing, because the beam forming requires your channel conditions and channel access available at the base station transmission. So you can look at this figure. This is one scenario at some time instant t equal t naught, or at some time instant t1. What happens immediately after a few milliseconds? After a few milliseconds, if you could see a pedestrian user, a very marginal or negligible difference has been made in his position. But look at a fast moving scenario where a user is residing within this vehicle. So here you need to form another beam for the vehicle. So for a vehicle, your channel duration is also very small because the channel is changing very abruptly. So whatever calculations you have been made for the previous channel condition cannot work for the next channel conditions. And in the case of fast moving user, the channel conditions becomes very changes very abruptly. So you cannot afford very high, very large computation, because at the time you make some computation in order to establish a communication. So if at the time you make some computation, the channel conditions may be changed. So frequent topology and millimeter wave requires pre-coder design, which outdate too soon in case of fast moving user. So therefore, fast moving users cannot be easily supported with the millimeter wave technologies. Why so? Because transmission computation time is very large. It would be easier to understand. So this is not appropriate for this discussion. Yeah. So let's say the time t is the duration where channel conditions are static. After this t, the channel conditions may change. So within this duration, all the computations done and pre-processing done for transmission can work in this duration only. After that, you need to perform again recalculation. So this frame defines here tt is the training time to get the channel conditions. TF is the feedback time. So first is the downlink training, then the feedback for uplink, and then data transmission. And you can look at this channel, or you can look at this slot. Within this duration, you are using only a smaller portion of data transmission, and first to TT and TF is for calculation and feedback only. So if this t is very small, that is the time duration, coherence time window is very small. That means the time where channel condition are static. If this is very small, you cannot afford to transmit TD because most of the time will be taken by TT and TF only. So in case of fast moving user, this coherence time is very small, so you cannot afford that. So what are the ways or what are the remedy for this? First one is dual function radar communication. So here what happens in case of a user, if the reflection body is too large, significantly large, as shown in this figure, here we are having one vehicle. If you can have reflection of that, you can utilize some radar technique to get some angle at which angle your user is being residing. So with the help of that angle of arrival, you can estimate where the next beam could be face. So the problem was you need to find the angle at which angle your beam could face in the next time slot, next transmission time slot. If you could have that information before the next time slot, you can save a little bit of time. So here the communication is being established between a car and radio frequency or radio waves are being sent towards the car. But here in this case, each base station is residing one radar unit. Radar unit means all the transmitted information. If you get some reflections back, you can estimate the angle of that. So in addition to the communication, the base station in this case, the with the radar compatibility are able to get the estimation of reflected waves. This is known as the concept of dual function radar and communication. So at some time instant Tn, it is establishing a communication, that is transmission is being carried out between the base station and the user, and also it is formulating this theta. That means the angle of arrival, so that the beam prediction should be done for the next time slot. So transmission for this time slot and calculation for the next time slot are priorly done. So this could save a small time so that this TT and TF could be minimized. So again, at T equal T1 n plus 1, communication is being established and beam predictions are being established for T n plus 2. So these are some methods by which you can save a small amount of time for the pre-processing. Now coming to the intelligent reflecting surface or smart environment. So is there any doubt with the DFRC scheme, dual function radar communication scheme? Anyone? So before we move further towards the last technique of this lecture, that is the intelligent reflecting surface, we have an announcement at 2 p.m. today. We are connecting with the Aryan Kaushik. Aryan Kaushik is an expert in 6G and most relevant aspect, for example, intelligent reflecting surface, dual function, integrated sensing and communication, and terrestrial network, space communication. He covers most of the next generation communication aspects, and also he is a big name in communication. So I request you all to be more attentive in the next session, please. At 2 p.m. we are connecting with Aryan Kaushik. We will also have a mail. We will also float a mail. So you must be presented there. Please assure your presence must at 2 p.m. lecture. Thereafter, we are having a lecture of Dr. Nishant Gupta at 3:30. So tomorrow's lecture we are rescheduling today, preponing that lecture today at 3:30. So today we are having 3 lectures, including mine, Dr. Aryan Kaushik, and Dr. Nishant Gupta. Tomorrow we will have 1 lecture in the afternoon. Okay. So if you do not have any query regarding this DFRC communication. Yeah, hello.
So I would have a doubt like.
Yeah. Please.
previous thing you are discussing, like dual detection of this radar. I would like to know what will happen if there is any false detections in that.
Yeah, yes. That's a very important question, I could say. Yes, the reflection could may occur from any other vehicle as well. Yes.
Yeah.
Yeah, some other vehicle may present at the so for this some mechanisms are being done. For first one is to cater the effect of false detection. Also, some feedback mechanisms are being involved so that the vehicle could not only this transmission, the vehicle could also transmit some of the signal. Some of the reflected entities. So some sort of hint should be there. Also some high resolution radars are being used so that you can have an accuracy of I could say some centimeters as well. So if you have an accuracy of tens of centimeters, 20 of centimeters, you can easily discriminate between the two vehicles, because usually the size of a vehicle is in meter range. So some high resolution are being performed, and if you receive multiple copies based on the prior detection and prediction, and based on the instantaneous velocity prediction of the vehicle, you can directly say that this wave is intended to my vehicle, and this wave reflected wave is intended to some other vehicle. So some mirroring methods are being implemented there.
Thank you, sir.
Any other question?
This is something like adaptive ways, any adaptive methodologies involved in that, so that.
Yeah, I have just given an essence of that, but that is not as simple as it looks. So this is based on some very large number of prior transmissions. So we cannot just say or predict the position of a vehicle with one computation only. We need to perform a large number of computation, and that's why it is known as predicted beamform. And so the calculation for theta n plus 1 depends not only on theta n or tn, it also depends on tn minus 1, tn minus 2, tn minus 3, and so on, so that the accurate decision could be made.
Thank you.
Any other question? Okay, so another lecture. Okay, so we will discuss. We will also discuss some of the queries that is being added in the message after the completion of this lecture. Okay, so now based on one request, I have put a small discussion regarding the intelligent reflecting surfaces, how it works. Beam estimation prediction. Yeah. So now not only the evolvement are being made at the transmission or the reception end, we are now working towards the smart environment as well. So here in this figure, you can see 3 reflected copies are being reached to at the receiver. So what happens within this communication transmission time? So let's say first copy of a receiver. First of all, the received copy or received signal is complex in nature, so it is having some magnitude and having some angle as well. So first copy, let's say, is having this much of amplitude. The length of this red one is showing amplitude, and the angle is showing the effect of delay and phase. So let's say first component is having this much of magnitude and looking at this angle. Next component is having some other magnitude and looking at some other angle. And last component is having some random magnitude and some random angle. So you cannot and we cannot control this angle, because we cannot control the position of a building, we cannot control the position of a vehicle, we cannot control the position of a user as well. So we cannot control anything, and we cannot also estimate this impact as well. So we have to have at the receiver end what happens, all such components are being summed up. So imaginary and real part are being summed up, and we get this. As a resultant of this imaginary and real part, the resultant becomes like this. So some of the component, as you can see here, are cancelling out each other. So for imaginary part are also positive and negative, positive and negative. These parts have been made up of real and imaginary part of the received component. So some of the components are cancelling out each other. So at the receiver end, we do not get the best we could have. So this sort of environment are known as dumb environment, because we cannot have any control over these reflections as well as at their magnitude as well. So we do not have any control there. That's why these environment are known as dumb environment. Now look at the smart environment. What could we have done? What else we could do? So these are the received copies. Can we have any control? So if you look at the figure, these waves have been reflected via some surface. If at the surface, at this building and vacuolar surface, if we could adopt some sort of processing or engineering to control the phases of them, can we have a better of it? Yes. We need to shift all such components towards the desired direction. So via assigning theta 1, theta 2, theta 3, in such a way that all the components should look in the same direction. So this is how the resultant would look like. The resultant will be having a larger magnitude as compared to the magnitude it was having in the previous case. So these environments are known as a smart environment. So any doubt with this?
Sir, is it similar to reconfigurable intelligent surfaces?
Yeah, this is the discussion. This is the same discussion. So at the surfaces, what we can do, so in order to calculate how much amount of theta or angle variation should be given, we should have the knowledge of that. And how we can perform the same, how we can achieve this, via making these reflectors intelligent. So buildings, cars, and all other environment, making such reflectors very intelligent and knowledgeable, which are having a knowledge of the amount of theta 1, theta 2, theta 3 should be given. We can adopt or we can achieve this. So with the available scenario, we cannot have any control. If the reflector becomes intelligent, we can have this. So how we can achieve that? The answer is intelligent reflecting surface. If we could cover all these surfaces with intelligent reflecting surfaces, so we can achieve this. So this is known as cophasing. Cophasing at the receiver, the reflection coefficient should be controlled in a manner that all the coefficients should look in the same direction. That's how the cophasing is done, and we could get a maximum of it. So intelligent reflecting surfaces are such surfaces. So intelligent reflecting surfaces usually cover large number of patches, and each patch works as a different reflector. So here we are having NH into NV number of patches. Each patch can perform their individual phase. So based on the required phase, each patch can control the angle of reflection or can control the phase of the reflection. And that's how you can achieve a cophasing at the receiver. So these are known as intelligent reflecting surfaces. So any doubt with this?
Sir, may I know about meta surfaces, intelligent, reconfigurable, intelligent meta surfaces, also a new term, I think. May I know about that meta surface?
Actually, intelligent surfaces are made up of surfaces which can control the phases. As such, we do not have any surface which can control or provide the controllable phase as of now. So we are working on their physics. At the background, what we are doing, we are controlling the equivalent circuits, capacitor and resistors. Because if you could see, a phase controller is made up of RC, that is resistor capacitor circuit, RL resistor inductor circuit. So these circuits which can control their capacitance and inductance are known as metasurfaces. Also, there is one term that is also very popular in terms of antennas, metasurfaces antennas, which can adopt their permittivity or permeability becomes negative. Those surfaces are also known as metasurfaces. Meta means a surface which is not naturally exist. So that's why these are known as metasurfaces. By applying some sort of physics or applying some sort of engineering, we make them enabling to perform such operations. That's why these are not true surfaces. These are engineered surfaces, and often metasurface term is being used for them.
Okay, sir. Thank you.
So this completes my discussion about 5G communication, latest technologies. Any other technology, if you want me to discuss about, you can request me. And if not within this series, we can conclude those lectures in the next series as well.
Sir, what is the meaning of this large training overhead in the IRS?
Yes. So if you could see this figure, here how many reflectors are there? 3. So in order to perform co-phasing, you need to control the angle of 3 reflections. But for doing that, you need to have a knowledge in which direction the reflections are being looking at this time. So to have that knowledge, you need to train the surface. The respective surface should have the knowledge in which direction the the respective component is looking. This is known as training, and training is done one by one. So if you perform the training for one surface reflector, your reflector 2 and reflector 3 should be silent. So in this case, you need to perform 3 trainings. Now coming to this surfaces usually cover how much number of reflectors? Thousands number of reflectors. So in the previous case, you need to perform 3 training. In this case, if you want to control all such angles, you need to perform all such training. That means 1000 elements means 1000 training. 2000 elements means 2000 training. Therefore, the training time is very large. And if the training time is very large, as we discussed before, we cannot afford to use such technologies for high mobility applications. Clear, sir?
Yes, sir. Clear. Thank you, sir.
Okay, next is how about multiple access technique like NOMA? NOMA I can cover. I will try to cover within this series. We can have one extra lecture. So tomorrow we are having one lecture only. We can. Sorry. So tomorrow, today we are having 3 lectures. Tomorrow we have one slot. If you want me to include NOMA and other aspect, you can request me with the next lecture only. I will cover NOMA. I can surely cover. If you want me to discuss NOMA, I will cover tomorrow. In the first lecture of tomorrow is free. I can take that lecture as well. So I will cover NOMA. You can also request me to cover other techniques if you want me to do so. Sir, would you like to know about the influence of AI in 5G, 6G? Yes, I will discuss this question later. First, I have my few lectures may be missed due to MTech lecture in second half. Will I be able to receive? Yes. So all of my lectures are straightforward. You will have access in a straightforward manner. No issue. And all other lectures, I will also try to provide you with the recordings if the experts allow. Now coming to the last question, that is, would like to know about the influence of AI and 5G, 6G. Okay, so as we have gone through the architecture of 5G communication, you can see here. So these entities which are residing beyond radio access network, 4G architecture may be more suitable to discuss this. Yeah, this core network in 5G, there are more number of entities. What are we trying to do? We are trying to shift the number of resources towards the cloud. That means towards the core network, so that the least capability would be available to the each cell site, just to reduce the cost, and more capability should be moved towards the uh, more capability should be available to towards the central unit, so that on demand we can we can perform, or we can allow users to use the resources. So in the fourth generation, we are having very less number of such flexibility. In the fifth generation, since resource pooling is done, virtual network virtualization concept is also there, and also this is only possible with the advent of AI. In the recent case, AI is the only solution which can adopt all such of flexibility and can provide all such of flexibility and optimization with respect to the time. So 5G will have a very much and great influence of AI for sure, and 6G for sure will have the influence where all the influencers which can influence 5G as well. Is that answer your question? Okay, so any more question? So I think it is already I had stretched a bit. So I will try to discuss about if you can do the lecture in the morning on NOMA and cooperative communication. I will try to do so. NOMA for sure I will include. I will try to include the second half. So I would request you to be more attentive in the second half session, which is at 2 p.m. today. So I request all of you to be present there. Dr. Aryan Kaushik, which is doing very good in the very short span of time. He is doing very good. So I request all of you to be more attentive with his class and into tomorrow's class as well. So if there is no more query, we can conclude this session. So thank you very much. Let's meet at 2 p.m.
Okay, sir. Thank you.
Okay, thank you.